In this lesson, we're going to be talking about protecting against buffer overflow attacks. So we've talked about buffer overflows and how those actually work and what it looks like in memory to trigger a buffer overflow. Now we're going to talk about what do we do to protect against buffer overflow attacks. So the first thing I'm going to show you is how to do it from a programming perspective. So I can show you the buffer overflow program again, just to remind you. And you can see there under the definition of the character array or the string, we've got this str copy. The str copy will just take a chunk of data and try to stuff it into a variable regardless of the size of either one of those variables there. So what I can do is I can replace that str copy with something called strn copy. And one of the nice things about Unix systems is the manual pages or documentation are included, including for programmers. So there's a function, I don't really remember how to use it. I can do man strn copy, and here's the manual page. And it actually includes str copy as well. So you can see the definition there is for a function that returns a pointer to a character, and strncopy takes a destination, a source, and a size. And it's that size that's the really important bit. So what I can do, I can go in and edit here and change this to strncopy. And then I can insert a 10 at the end. And what that's going to do is it's going to say, once you have copied 10 characters or 10 bytes, you should stop. So it gives me some control over the amount of data that I have actually copied. And I can make sure as a programmer that I only copy enough data to fill the space that I have allocated. So I don't try to copy more data than I have actually allocated to a particular variable. So that's something I can do on the programming side. So we've got this memory layout, and I can't rely on all programmers to go do the right thing. And there's certainly a lot of programs that have been written over the years that are vulnerable to this that are not going to be rewritten for a variety of reasons. So there are probably some things that we should think about doing to protect the operating system. And those are things that we can do in the operating system kernel in order to protect the system and keep applications from doing bad things. So one thing that we can do to protect against buffer overflow attacks is the portion of the memory layout in low memory where all of the executable portions of the program are, that should be the only thing that actually can be executed. So when we get to the portion of the memory layout where the stack is, the operating system should say, hey, that's a stack and nothing out of there should be executed. So we should protect against buffer overflows by making sure that the stack is non-executable, meaning you can't inject code into the stack and then manipulate the return pointer so that it points into the stack and executes the program code that you have just uploaded in. So we should make the stack not executable. That's one way of doing it. Another thing that we can do is we can randomize the memory locations. So the way it used to be was every time you ran a program, you were pretty much guaranteed to get the same memory allocation. Since all memory allocations are virtual, you're not being given real memory addresses. You've just got a virtual address that the operating system manages and does the translation back to the real address. Since we've got virtual addresses, what we can do is randomize the starting point of the memory that you are given. So every time you run the program, your program is going to be given a different address space. In other words, when you run the program, you can't always guarantee what an address is going to be. And that's one way buffer overflows worked pretty well, was they could predict where the program was going to be at any given point and know the memory location that they needed their return pointer to point to. So if we've randomized particularly the stack for the memory layout, every time they run a program, it's going to have a different memory address. So it's going to make it a lot harder to figure out where they need to set that return pointer to execute the code that they have stuffed into the stack. So that's something else they can do. And you certainly see modern operating systems are doing stack randomization because it's something that they can do and that they have some control over. So they do stack randomization, where they randomize the layout of the stack and the addresses that you're provided. So there's something else that can be done, and it's kind of an interesting concept. It's something called a stack canary. And you may have heard stories about the canary in a coal mine, where coal miners would take a little caged canary down into the coal mine with them. And the reason for that was because the canary is a particularly sensitive bird. And if there were gases in the coal mine that were being released from their mining activities, the bird would die from these toxic gases. And when the miners noticed that the canary was dead, they knew it was a signal that they needed to get out of the coal mine, because there were gases that they may not be able to smell, and so they could soon be dead as well if they didn't get out. So it was a signal to get out. So a stack canary is where we place a piece of data in front of the return pointer. So you can see there in the stack frame, function local vars base pointer return pointer. What we would do would be to place a piece of data in front of the return pointer that we knew about ahead of time. So when it comes to returning from the function, we would check the stack canary in memory against the stack canary that we knew that it should be. And if the values differed in any way, there was a pretty good chance that the return pointer had been corrupted in some way, and we should just dump out of the program. We should get out of the coal mine. So that's a stack canary. That's where you put a piece of data in front of the return pointer and then do value comparisons to determine whether you think the return pointer has been corrupted or not. So that's another way that we can protect the program and the operating system from these buffer overflow attacks. But that's a few different ways that you can manage protection against buffer overflows and buffer overflow attacks.